Hello everyone and welcome to lecture 12. Today we're going to talk about multiplication in hardware. So last time we looked at finite state machines. We're approaching the end of part 1 of this course. We have a few more lectures left. We said that a finite state machine was a logic block that has inputs, outputs, and some state inside of it. And there's two parts of the finite state machine. One part that computes the output based on the input and the state, and another part that computes the next state based on the input and the current state. And this was kind of a schematic of what a finite state machine looks like. We have the state, we have an output function that computes the output, we have a next state function that computes the next state, and that goes all the way back and comes in as an input for the state. The state is usually a flip-flop of some kind, such that on the active edge, the next state computed by the next state function becomes the current state for the next cycle. We said that for the finite state machines we're looking at in the course, we were only going to consider finite state machines where the output is only dependent on the current state. It's not dependent on the input. And we looked at an example. We kind of solved together an example of a finite state machine that controls an intersection. It has two sensors that tell it whether there's a car on the north-south road and the east-west road, and has two outputs that tell the north-south light to turn green or red and the east-west light to turn green or red. And we looked at the rules that we wanted the finite state machine to enforce. These included, when are we going to turn green and on which intersection. We then drew a state diagram that fulfilled the rules that we specified. And the state diagram consists of different states that the finite state machine could be in, the output for each of these states, and also the transitions between states that are going to take place for every combination of state and input. And with that, we went from this state diagram to a truth table for our output function and a truth table for our next state function. And from these truth tables, we extracted these equations. Of course, you usually use a Carnot map to simplify the equations, but we skipped that step because we already know how to use Carnot maps. So we got equations for the output function and the next state function, and using these equations, we built our finite state machine where the output was based on whatever function we applied on the current state, and also the next state was based on what this next state function that is applied to the inputs and the current state. So this is what we covered last time with regards to finite state machines. Any questions about what was covered before we move on to today's lecture? Okay, well, if there are no questions, then today we're going to talk about multiplication in hardware. So I'll start, before talking about multiplication, I want to introduce a simple concept, and that is the concept of shift registers. So what are shift registers? A shift register is an array of cascaded flip-flops that share the same clock, and where the output of one flip-flop is the input to the next one. So here we have a flip-flop. The output of the first one is the input to the next flip-flop. The output of the second flip-flop is the input to the third. The output of the third is the input to the fourth, etc., until we reach the last one. And all these flip-flops are driven by the same clock. Okay. So now what happens when we have a shift register like this? Well, what happens is I'm first going to have an input here. And then on the next cycle, the input that was here will come here. And I'm going to have a new input here. And on the following cycle, the input that was at the output of the first flip-flop will come to the second flip-flop. The input that was at the input of the first flip-flop will now become the output of the first flip-flop. And I'm going to get a new input. And so on. So in the following cycle, the output of the second becomes the output of the third, the output of the first becomes the output of the second, and then I'll get a new value coming in. So essentially what a shift register does is that the value that is stored inside of this shift register is going to shift by one every cycle. Now, in this specific implementation, the value is going to shift right every cycle, okay? So we have this sequence of bits, and the sequence of bits is going to shift by one every cycle. And the reason I'm introducing shift registers is that they are useful for implementing multiplication and division. So is it clear to everyone what a shift register is? We're going to use it, so you'll see an example of how it works. But is the concept clear? Any questions? Okay, great. So now let's start talking about multiplication. So if you remember, I'm going to review how we did multiplication in binary before. Oh, someone's asking if it wraps around. It just depends on how you implemented the shift register. You can implement a shift register that wraps around. You can implement one that does not. Okay, so for here, I'm just interested in the general concept of the shift register. What exactly happens at the boundaries, differs between how you're using the shift register. Okay. Okay, so if we remember, the way we did multiplication was as follows. If I had two numbers that I wanted to multiply, what I did is I multiplied the first number, called the multiplicand, by the least significant bit of the second number, which is called the multiplier. Okay, we got this. Then we multiply it by the second bit, and we get the result, but shifted. We multiply it by the third bit. Here, in this case, the third bit is 0, so we're just going to get zeros, and they're also going to be shifted. And then we multiply it by the fourth bit, and the fourth bit is 1, so we're going to get the value of the multiplicand 1101, and that's also shifted one more place value. So after doing this, after multiplying the multiplicand by each bit of the multiplier, we get these numbers that are shifted according to kind of the place value. So the next step we did was we added these four numbers. So we add these four numbers and we get our final product. So the product of the multiplicand and the multiplier here is this value down here. Okay. It's very important that you understand this, and we covered this before. Does anybody not understand this? Do I need to re-explain this one more time? It's very important that you understand how multiplication works for this lecture. Okay, great. So it's clear to everyone. And the question is, how do we implement multiplication in hardware? So how can I do this procedure that I did to multiply two numbers? How can I implement hardware that does this for me? Okay, so to implement this in hardware, I have a few observations and also a few kind of modifications to the way we're thinking about things. We're going to do the same thing, but we're going to think about it a little bit differently, okay? So the first observation is that if I'm multiplying two 4-bit numbers, then the product of these two 4-bit numbers can have up to 8 bits, okay? So the product of the two 4-bit numbers can have up to 8 bits. So what I'm going to need is I'm going to need an 8-bit register to store my product. Okay, so that's the first observation. The second observation is that to find this product, multiplication is simply the addition of multiplication of two 4-bit numbers is simply the addition of these four 8-bit numbers. So I can implement multiplication using addition. I already know how to do addition. I already know how to implement hardware that does addition for me. We saw that before. So what we're going to do is we're going to leverage the hardware that we built for addition in order to implement multiplication. And in this case over here, to multiply two 4-bit numbers, we're going to use an 8-bit adder. We'll improve on this later on, but for now, we will use an 8-bit adder, okay? So the way we're gonna do multiplication is by adding four 8-bit numbers. The way we would do a 4x4 multiplication is by adding four 8-bit numbers. Okay, now if I want to add four different numbers, the addition hardware that we've looked at so far cannot add four numbers simultaneously. We've only implemented an ALU that can add two numbers at a time, right? We've only implemented an ALU that can add two numbers at a time. But here what we want to do is we want to add four numbers. So what we're going to do is
2n-bit ALU.
Sorry?
N-bit ALU for summing two and another for summing the other two. So we need like three ALUs.
So we can use three different ALUs, or we can use one ALU and use it four times. Okay, so we need to do, rather than doing one addition of 4 inputs, we're going to do 4 additions of 2 inputs, okay? So here's how we're going to do it. We're going to initialize the product to 0. Then we're going to use a 2-input ALU to add 2 numbers and get the result. And then we'll use another 2-input ALU, or maybe the same ALU, we'll reuse it to add those 2 values and get the result. And then we do another addition, add these 2 values and get the result. And then we'll do a final addition and add these 2 values and get the result. Okay? So rather than adding four numbers at once, we're going to convert that into 4 additions of 2 numbers. Okay. So I'm just I'm kind of thinking about how I can use the adder that we've implemented that can add 2 numbers in order for us to implement multiplication. All right. Any questions so far? Okay, so there's one more thing that I'm going to change about the way I'm thinking about multiplication. The result for practical purposes is the same, but I'm going to change the way I'm going to think about it a little bit. So here, what we're doing over here is we're adding, take this number, this partial product, and we add 0 to get a new partial product. So here, rather than thinking of adding 0, the way I'm going to think about it is I'm going to keep the multiplicand here shifted. So I'm going to think of this as this multiplicand that was originally there shifted. So I'm going to add this multiplicand, but then rather than storing the result as the new partial product, I'm simply going to deactivate writing this value and keep the original product. Okay. So rather than adding 0, I'm going to add the shifted multiplicand, but I'm not going to store the result. Okay. And to do that, what I'm going to do is I'm going to use the bits of the multiplier to decide when I'm going to store the result and when I'm not going to store the result. So here the multiplier is 1, 0, 1, 1. So I'm going to use the rightmost bit as kind of the decision whether or not to write for the first addition, the next bit as the decision whether or not to write for the second addition, the third bit, which is 0 in this case, as the decision not to write for the third addition, and in this case we're not going to add, and then the fourth bit as the decision of whether or not to write for the fourth addition. Okay, so I'm doing the exact same thing, but I'm thinking about it in a different way. Rather than adding 0, I'm going to add the shifted multiplicand, but I'm not going to store the result, which for practical purposes is the same as adding 0. Okay, any questions so far? Okay, so now that kind of we've formulated our multiplication in this way, if you observe, the strategy that we're going to use for doing multiplication in hardware is as follows. We're going to shift our multiplicand by left every cycle, and we're going to add it to the product. So we're going to initialize the product to 0. We're going to add the multiplicand, and then on the next cycle, we're going to shift the multiplicand and add it to the next partial product to get the result. Then we're going to shift the multiplicand, add it, and then we're going to use the multiplier bit to choose whether or not to update the product. Okay, so this is our overall approach. Every cycle, we're going to shift the multiplicand left. We're going to add it to the partial product, which is initialized to 0. And we're going to use the multiplier bit to determine whether or not to write the result. Okay, so now let's implement hardware that does this. First, we're going to start. We need a register to store the product. How many bits should this register have? So the product register is going to have 8 bits exactly. Okay, so we're going to need a product register that's going to be 8 bits long. We're going to have the multiplicand, and we're going to shift it left every cycle. So we need a register to store the multiplicand. How many bits should I use to store the multiplicand? Even though the multiplicand is 4 bits, I'm going to need to shift it left every cycle for 4 cycles. So I'm going to need a total of 8 bits to represent it. So we're going to store the multiplicand as 8 bits. And then what we need is an ALU in order for us to be able to add Well, first of all, we said we're going to shift the multiplicand every cycle. So we're going to have a controller that's going to send a signal to the multiplicand and tell it to shift left every cycle. Okay, so here this is a controller. The controller is telling different registers what to do. And in this case, the controller is going to tell this shift, we're going to use a shift register to store the multiplicand. And the controller will tell the shift register to shift left. Okay. All right, and then we said we want to add the multiple every cycle. We want to add the multiplicand to the product and store the result as the new product. So what we're going to do is we're going to have an ALU, and this ALU is going to have two inputs. One input is going to be the multiplicand, and the other input is going to be the product. And the controller is going to tell the ALU to perform an addition. Okay, and then what do we do with the result? Where do we store the result? We're going to store the result as the new product. Okay, we're going to store the result as the new product. So here on the diagram, we added the product to the multiplicand and we stored the result as the new product. Okay, so this is what we're doing over here. Okay, we're updating the product, and notice that this update is going to happen at the end of the cycle. So here, during the cycle, we're going to be reading the product in order for us to add it to the multiplicand and get the sum. But this sum is going to wait here. It's not going to be written. When does it get written? It gets written at the end of the cycle as the new product to be used for the next cycle. So here, obviously, it's important that we're using flip-flops to implement the product register in order for us to make sure that we don't write the result until the end of the cycle. Okay, and then there's one more thing. We said we're going to use the bits of the multiplier. Okay, we're going to use the bits of the multiplier to decide whether or not we're going to write the partial sum as the new product. Okay, so how do we do that? Well, we're going to have a register that's going to store the multiplier. And on the first cycle, we want to use the leftmost bit. On the next cycle, we want to use the second bit. On the next third cycle, we're going to use the third bit. On the fourth cycle, we're going to use the fourth bit. So what we're going to do is we're going to shift the multiplier right every cycle and always use the last bit. Okay, so here the last bit is going to be this one over here. On the next cycle, we'll shift it left so that the last bit becomes this one over here, and we'll use this one. And we're going to give this last bit to the controller. And based on this last bit, the controller is going to tell the product register whether or not to write. Okay, so here, if this last bit here was 1, we're going to write. If the last bit here was 0, we're not going to write, which is equivalent to adding 0. Okay, let's do an example. So this is what the multiplication hardware looks like. But now let's do an example to make this more clear. So what we're going to do is we're going to initialize the product to 0. So here the product is initialized to 0. And then here the product register is initialized to 0. We're going to initialize the multiplicand register to 0, 0, 0, 0, and then the value of the multiplicand. So here we have 0, 0, 0, 0, 1, 1, 0, 1. So we'll store that here as the multiplicand, 0, 0, 0, 0, 1, 1, 0, 1. And we're going to initialize the multiplier register to the value of the multiplier, which is here 1, 0, 1, 1. Here we have 1, 0, 1, 1. And what's going to happen during this cycle is we're going to read the value of the product, and we're going to add it to the multiplicand, and we're going to get the result, which is this value down here. And this result is going to sit here at the input to the product register, and it will be written at the end of the cycle. Okay, it will be written at the end of the cycle. So when the end of the cycle comes, what happens? This value over here becomes now the new product. So now I have 0, 0, 0, 0, 1, 1, 0, 1 as the new product. My multiplicand register is going to be shifted left once. So here we shift left between here and here. So that's what happened here. This register got shifted left. Okay. And now I want to use the second bit to select. So you can think of this as shifting our multiplier right by 1 bit. And that's exactly what happened here. The multiplier shifted by 1 bit. And now I'm using the second one over here. We give that to the controller. The controller uses that to tell the product register whether or not to write. Okay. Now, when I do the addition of the product and the multiplicand, here the product and the multiplicand, I get the result, but the result sits at the input of the product register and does not get written until the end of the cycle. Okay. Now, at the end of the cycle, this value of the product here, 00100111, is going to get written as the new product. Okay, so now we have the new product over here. And we're going to take that and we're going to add that to the shifted multiplicand. So here the multiplicand is shifted left again, and we're going to add these values together. And what we're going to do is this value is going to sit here at the input to the product register. But this time, the bit that is controlling whether or not I write is 0. Okay, so because here I shifted my multiplier right again. So now I have a 0 here as the bit controlling this addition. And because I have a 0, the controller is going to tell the product register not to write on this cycle. So what happens is I've done the addition, but I'm going to discard the result. I'm not going to write it. And by doing that, this is as if I added 0. Okay. And then finally, on the last cycle, I will take my product, which is not going to change, and I'm going to add it to the shifted multiplicand again. I get the final, I get this result over here, 1, 0, the sum, because over here we have a 1, so we're going to write. Okay, and then finally, on the last cycle, once we get the sum will be written as the final product, and now I have the result of the multiplication. Okay. Any questions about this? Is it clear how we've done multiplication in hardware? Okay, great. All right, so let's see how much this hardware multiplier costs. Let's take a look. So in general, if we're doing an n-bit by n-bit multiplication, we're going to need a product register. If we use this approach, we need a product register that's 2n long. We need a multiplicand register that's also 2n. We're going to need a multiplier that's n bits long. And we're going to need an ALU that can add 2n bit numbers. Okay, or 2 numbers that are each 2n bits long. Okay. So what is the total cost? Well, we have 2n for the ALU, right? We need a 2n bit adder. We need 5n bits for registers. So we have 2n register plus 2n register plus an n bit register. So here the cost of the registers is 5n. And of course, the part of the cost is not just the hardware, but also the time it takes. So how many cycles does it take to do this addition? Well, it takes n cycles. If I'm multiplying 2 n-bit numbers using this multiplier over here, I'm going to need n cycles. So this is my cost, 2n ALU, 5n registers, and n cycles for time. The question is, can we do better? And there's two parts of this question. What do I mean by better? Do I mean less hardware, or do I mean faster? And both of these are valid questions. So we're going to look at both of these questions. Can we use less hardware to perform this multiplication in the same amount of time? Or can we perform this multiplication faster, even if this means using more hardware? Okay, so this is what we're going to look at. So let's first look at using less hardware. Before I continue, any questions so far?
Sir, why is the multiplicand 2n?
Why is the multiplicand 2n? So let me go back. So remember here what we did, the multiplicand was 4 bits. So we needed 8 bits to represent it because we were shifting it one cycle by 1 bit every cycle.
Oh, yeah, true.
So that's why we needed 2 n-bit because we have n bits, but we also have n cycles of shifting. So we need 2 bits total to represent it. Okay.
Okay, thank you.
Yep, you're welcome. Okay, any other questions? All right, so let's see how we can use less hardware to do this. So what I'm going to do this time is I'm going to think about my multiplication a little bit differently. So what we observe is that even though I'm using 8 bits to store the multiplicand, only 4 of these bits are useful at any given point in time, right? So the multiplicand is only 4 bits, And these shifted values, only 4 bits in this 8-bit register are useful on each cycle. The rest are always 0. So really, it's a waste of space to have to store all these zeros. So that's the first observation. The second observation is, even though I'm doing an 8-bit addition here, right? Even though I'm doing an 8-bit addition, really the only bits that matter during this addition is 4 bits, okay? Because here I only have 4 bits that are useful each cycle. The others are zeros, right? So having an 8-bit ALU, 4 of the bits that are coming into this 8-bit ALU are going to be 0. So four out of the 1-bit adders are just going to be adding 0. They're not going to be doing anything useful. Okay. So only at every cycle, only a 4-bit window of the product is going to be added to the multiplicand. And so we really only need a 4-bit ALU to perform this addition. It's overkill to have to spend an 8-bit ALU. Okay. And we can think of this product, even though the product still has to be 8 bits, since we're only adding 4 bits of the product each cycle, and these 4 bits are shifted this window of the 4 bits that we add is going to be shifted left every cycle. We can think of the window as being shifted left into the product, or we can think of the product as shifting right every cycle. So if we think of this window as stationary, the product is shifting right with respect to this window every cycle. Okay, the window is shifting left with respect to the product. The product is shifting right with respect to the window. Okay, so here we only need a 4-bit ALU to do the addition, and we only need 4 bits to store the multiplicand. So based on these observations, again, the bits here to the left are always 0, so we don't really need to store them. It's a waste to store them. Okay, so based on this observation, let's see if we can build a more efficient multiplier, and the answer is we can. So we're going to change our strategy for multiplication. We're going to keep the multiplicand fixed. Okay, we're not going to shift it. We're just going to have, we're going to think of it, you're going to think of this window. We're going to think of the register storing this window as opposed to storing the entire multiplicand. And we're going to keep the multiplicand fixed. We're going to think of the register as also storing this window over here. And in this case, we're going to shift the product to the right every cycle. And the multiplier is going to be the same. We're going to use the multiplier to choose whether or not we're going to update the product or not. Okay, so let's take a look at what this means in terms of hardware. The multiplicand this time is going to be 4 bits. Okay, not 8 bits. And it's not going to be shifting. It's going to remain stationary. The product this time is still going to be 8 bits, but we're logically going to think of the product as having 2 parts, a 4-bit window, and then kind of 4 bits that are to the right of the window. And this time the product's not going to be stationary. The product is going to be shifting right every cycle. Okay. As for the multiplier, nothing has changed. It's going to shift right every cycle, and we're going to use the least significant bit of the multiplier to decide whether or not to write to the product register. Okay. Now let's look at how we can use this hardware over here to do the multiplication. We're going to initialize the multiplicand to 1101, and it's going to stay like that. And we're going to initialize the window part of the product register to this window over here, 0000. And then to the right, these values over here to the right correspond to kind of this void over here. So there's nothing really interesting here. There could be a 1, there could be a 0. We're not really interested about what's going on over here. Okay. So what happens in the first cycle is we're going to add this 000 to the 1101 of the multiplicand using a 4-bit ALU, and we're going to get the result, which is going to be 01101. Okay, and then what's going to happen? And then this is going to be our result. And on the next cycle, this result is going to be kind of stored but also shifted. Okay, so on the next cycle, my value is 01101. Okay, and then the least significant one of the product is now shifted outside of the window. So here now my window has shifted left 1 cycle, sorry, one position, or you can also think of it as the product shifting right one position. Okay, so now my window in the product is shifted, or my product shifts right. The multiplicand is still going to be the same. It's going to store 1101. And now I'm going to add this window over here, the 0110, to my 1101. So this 0110 is going to be added to my 1101 using the 4-bit ALU. The result is going to be 10011. And what's going to happen now is I'm going to write this result, but also shift it by 1 when I write it. So this 1 here is going to be shifted over here. This 1 here is going to be inserted and shifted. And then this 1001 is also going to be inserted and shifted, such that on the next cycle, the window now has 1001. Okay, so now the window is here, right? And I have these two ones, which I don't care about during the addition. And these two ones are going to be outside over here. And now I'm going to add this 1001 to my multiplicand. Okay. However, this time, because the multiplier bit is 0, here the multiplier is shifting right every cycle. Because the multiplier bit is 0, I'm going to do the addition, but I'm not going to store the result. So that's equivalent to multiplying by 0. Okay. And that's why I'm going to take this window, I'm going to do the addition, but then I get the result, but I'm not going to store it. Instead, I'm just going to keep this value over here that I have, but of course, I'm going to shift it by 1 cycle. Okay, so here I'm going to shift the value by 1 cycle for the next cycle. And then in the final cycle, now my product window is here. I'm going to add these 4 bits, 0100, to my multiplicand, which is still 1101. Right, and then I'm going to get the result of that addition, and that's going to be 10001. And on the finals, and because my most significant bit here is 1, here the bit is 1, I'm going to write this result and shift it. So I'm gonna, the 10001 is going to get written. I'm going to have here 10001, and then the 111 that I had from before are shifted to the right. Okay, and by doing this, I have the final result over here that I'm looking for. So any questions about this strategy?
Sir?
Yes.
After the controller, we have an arrow عليه add. Doesn't that mean إنه if we have like in the number in the 4-bit multiplier اللي تبع shift right واللي بيعمل multiplication إنه إذا كان 0 it won't add it at all?
Here we have add. Okay, so the ALU is always going to add, right? But what's
not according to the result of the controller. Like if it is 0 here, and the controller would be 0, and اللي طالع على الاد هو 0. Doesn't that mean it won't add?
No, the controller. So the controller, so this bit over here is fed as an input to the controller. The controller is going to use this bit to tell the product register not to store, but that does not affect what the controller tells the adder.
But isn't it إنه طالع كresult منه الcontroller إنه الاد isn't affected by the controller?
No, the controller doesn't have. If this is 0, the controller doesn't have to give 0 to every as all its output.
Okay.
Right? Just because they have 0 coming into the controller doesn't mean all the outputs of the controller have to be 0. Okay.
إنه it's manipulated إنه inside, right? Like
yeah, the controller is going to use this bit, right? Inside, the controller is smart. It knows what to tell everyone to do. So the controller is going to use this bit to tell the product register what to do, right? But it's always going to tell the multiplier. If we're doing multiplication, the controller is always going to tell the ALU to perform an addition.
All right, thank you.
So you might be asking, you might be thinking, okay, let me go to the end. You might be thinking, okay, why do I even need this add signal over here? Why can't I just put an adder over here and always do addition? Why do I need a controller? So maybe that's a source of confusion. The reason is that we're going to use the same hardware to do division. And with division, we're going to do subtraction and not addition. So that's why I have the controller here has a control signal that's telling the ALU to add. Because if I'm doing the division, the controller is going to tell the ALU to subtract and not add. Okay, but if we ignore that, if we don't think about division, for the purpose of multiplication, this ALU is always adding. So you can think of it as just an adder.
Okay.
Okay.
Thank you.
Yeah, you're welcome. Any other questions? Someone's asking, when we write the product, do we write only in the left 4-bit window? Yes. So let me go back maybe a few steps. So over here, when we're doing this addition, right, this 1, 1 over here is logically being added to 0, 0. So this 1, 1 here is never going to change. It's going to stay 1, 1. And that's why there's no point in performing an addition. Okay, so that's why this 1, 1 over here is not going to be touched. It's just going to be shifted. The 4 bits that are affected by the addition are these 4 bits here in the window, 1, 0, 0, 1. So that is why we only read the 4 bits in the window when we do the addition. And then for the final result, when we add 1, 0, 0, 1 to this 1, 1, 0, 1 over here, it's impossible for us to affect these 2 bits. Right? It's also impossible for us to affect this bit here on the far left. The only bits that are possible to get affected by this addition are these 5 bits here: 1, 2, 3, 4, 5. Okay, so that is why when we get the result of the addition, we get 5 bits, right? And then when we store these bits to the register, the 4 leftmost bits are going to become the bits inside of the window for the next addition, and then the 5th bit is going to be kind of the new bit. Well, it doesn't show here, but for this case over here, the 4 leftmost bits are going to be the ones that will go inside the window, and then this 1 over here is going to go to the right over here. Okay. So we always read a 4-bit window. Our result is going to be at most 5 bits. Only 5 bits are going to be affected, but only 4 of those 5 bits will be useful on the next addition. And that is why the window remains 4 bits. Okay, any other questions? All right, can we do something better? I'm going to replay this addition, this multiplication, and to show you that we can do something slightly better, actually. So here, this was where we started. We had 4 bits of the multiplicand. These are stationary; they don't move. We have this 8-bit product register that initially has 4 bits. And we're going to shift these right by 1 every cycle. And then we have this multiplier over here, which is initially 4 bits, and we're also going to shift these right by 1 every cycle. So one observation is that the number of unused bits in the product is equal to the number of used bits in the multiplier. So here in the first cycle, we have 4 bits in the product register that are not used. And we have 4 bits in the multiplier register that are used. On the next cycle, we're going to shift the product by 1, and then we're going to shift the multiplier by 1. So in the next cycle, we're going to have 3 bits in the product register that are not used. And we're going to have only 3 bits in the multiplier register that are actually used. Okay? On the next cycle, we're going to have 2 bits in the product register that are not used, and 2 bits on the multiplier register that are actually used. Okay, next cycle we have 1 bit that's not used and 1 bit that's actually used. And in the final cycle, we have no bits in the product register that are not used. All the bits are used, but we also have no bits in the multiplier register that need to be stored. Okay, so given this observation, what do you think we can do? If we want to save on the number of registers, what can we do based on this observation?
We can start by storing the multiplier on the right part of the product.
Yes, exactly. Well, that's exactly what we can do. We can take the bits of the multiplier and store them in the right part of the product. And every cycle, we're going to be shifting the product right, and we're going to be shifting the multiplier right. So the optimization is we're going to reuse the same register for the multiplier and the lower half of the product. So let's see what that looks like. We're going to do this. We're going to put the multiplier here. Okay, and we're going to initialize the product here. And on the next cycle, the product's going to be shifted by 1, and the multiplier is going to be shifted by 1. And on the next cycle, the product will be shifted by 1, and the multiplier shifted by 1. The next cycle, the product will be shifted by 1, the multiplier will be shifted by 1. And in the final cycle, we have the final product that we're looking for and we've destroyed the multiplier. It's no longer there, but that's fine because we no longer need it. Okay, is that clear to everyone? Any questions about this? Okay, so given this implementation, let's see how much this implementation costs. So in general, we're going to need an n-bit, if we're doing an n by n multiplication, we're going to need an n-bit ALU, an n-bit register for the multiplicand, and a 2 n-bit register for storing the product and the multiplier. Okay, so the cost for the first design was a 2 n-bit ALU, 5 n registers, and we needed n cycles to do the addition. The cost for the second design is what's the ALU cost? Well, we need n 1-bit ALUs. So the cost of the ALU is n. Okay, what about registers? What is my register cost in terms of n? Right, it's going to be 3n. So now we have half the number of 1-bit ALUs, right? And we've reduced the number of bits or flip-flops that we need from 5n to 3n. Okay, what about time? Has the time changed? It's still n. So we still need n cycles. So both the first and the second design need n cycles to complete. But as you can see, the second design is able to perform the same operation in the same amount of cycles, but using substantially less hardware, almost half the amount of hardware. Okay, and this is a good example of how sometimes the most intuitive way of thinking about an operation is not necessarily the most efficient way of implementing that operation in hardware. Okay. All right. Now let's kind of look at one final thing. So can we do better? Can we go faster? So can we, if we care about speed, we don't care about hardware cost. If we care about finishing the multiplication as fast as possible, even if that means using more hardware, can we go faster than this? And the answer is we can. So if we go back here, we said that the multiplication is equivalent to adding 4 8-bit numbers here in this example here. And what we did in the first two designs is we used an 8-bit adder, and we used that 8-bit adder 4 times in order for us to add these 4 numbers. Well, what we can do is rather than using one adder, we can use multiple adders and have these adders work in parallel. And this is another design that can be used to implement multiplication. What we can do is we can add these 2 numbers together using an adder, and we can have another adder that at the same time will add the third and the fourth number together. So we add the first and the second together with one adder. We add the third and the fourth together with another adder. And then now we have these 2 partial products. And what we're going to do is we're going to use another adder to add these 2 together to get the final product. Okay. And since we're going to have we're going to use different adders, right? We're going to be able to finish we invested more hardware, but we're going to be able to finish in less time. Okay. And specifically, how much less time? Well, okay, before we kind of do the analysis, let's see how to implement this. So what we're going to do is here we only care about these 4 bits when we're doing this addition. So we only need a 4-bit adder to do this addition. And here the only bits that we care about adding are these bits over here. The others are just going to be adding zeros to zeros. So we're going to need a 4-bit adder to add these 2 bits over here. And then we're going to get the partial products. And when we add these 2 partial products, we know that these 3 bits are going to be zeros. So we don't need to have an adder to add these ones. We just care about these bits over here. So we're going to use a 4-bit ALU to add these 4 bits to get the final product. And that's exactly what's going on here. We have an ALU to add these 4 bits, an ALU to add these 4 bits, and then an ALU to add these partial products to get the final product. Okay. So how much does this adder cost? In general, if we have an n-bit value, we're going to have, these ALUs that will be reduced by log n every time. So we're going to start with n over 2 ALUs and then n over 4 ALUs until we get to 1 ALU. So if we go, this was the cost for the first and second design. For the third design, how many ALUs do I need? Well, I need a total of n times n minus 1 ALUs. Sorry, I need n minus 1 ALUs. That's n over 2 plus n over 4 plus n over 8 plus n over 16, etc. And then each of these ALUs is going to be n bits wide. So the ALU cost is going to be n times n minus 1 1-bit ALUs. Okay, but then what is the time that I need to do this addition?
Something log.
Right, it's going to be log 2 of n, exactly. It's going to be log 2 of n, and more importantly, here, this n, it refers to n cycles. Okay, this n refers to n cycles. Over here, it's log 2n, but I actually don't need to. I don't need to kind of store. I don't need to, do these additions in one cycle and then these additions in another cycle. I can actually do the entire multiplication in just one cycle. Okay, so this needs n times. So this needs n additions. This needs log n. It's not log n additions, but log n additions sequentially. But also these log n additions can be done in one cycle, whereas these n additions, each addition needs to be done in a separate cycle because we're reusing the same ALU. Okay, so this is an example of how we can invest a lot more hardware, but be able to get do the operation a lot faster. Okay. Any questions? Okay, well, if there are no questions, you can read more about multiplication in section 3.3. There's also section 3.4 that talks about division, but we're not going to cover division in this course because we don't have enough time. But division is actually very similar to multiplication, but rather than constantly adding the multiplicand based on the multiplier bits, what we're actually going to do is we're going to constantly subtract the divisor from the dividend and extract that result to be the final quotient. Okay, so division is very similar. We're going to be also doing this shifting, and we're going to be subtraction instead of addition. You can read about it more in the textbook if you're interested, but for this course, you're not required to worry about it. Okay, that's all for today, and I'll see you next time. Bye, everyone.